the past several lectures, I've been talking about the properties of materials. And we've seen that all material properties in one way or another are dependent on the atoms and how those atoms are fit together. Lecture 27 marks a transition of sorts. 2 lectures from now, we're going to talk about stars, which are the largest material objects in the universe, the largest collection of atoms that we know. But first, we need to look at the atom in a bit more detail. In fact, look at the nucleus of the atom. We're going to find that radioactive atoms spontaneously disintegrate, releasing energy in the form of high-energy radiation. I'm going to begin this lecture by reviewing the nature of the atom and its nucleus. The nucleus has 2 kinds of particles, the protons and the neutrons. Then I'm going to introduce the concept of an isotope. An isotope is an atom in which we know both the number of protons and the number of neutrons. And I'll discuss the table of the isotope, which systematizes all the different known isotopes. We're going to see that isotopes can experience a number of different fates, including radioactivity, by which the atom's nucleus emits energetic radiation. There are 3 different kinds of radiation: alpha, beta, and gamma. And I'll look at some of the dramatic consequences of radioactivity as well. Let's begin by reviewing the structure of the atom. Recall the Bohr atom. In the Bohr atom, there's a central, massive, positive nucleus, a nucleus that contains positive protons. And orbiting around that nucleus are electrons. So far in chemistry, we've talked about the behavior of electrons, how they interact. As scientists of the late 19th century explored the properties of more and more different elements and compounds, they discovered the astonishing and the completely unexpected ability of certain elements to give off nuclear radiation, intense amounts of radiation, spontaneously. This nuclear radiation, in the context I'm talking about, is any energetic particle or wave that suddenly and spontaneously is emitted from an atom. The discovery of radioactivity and the subsequent exploration of the atomic nucleus eventually led to the fields of nuclear physics and nuclear chemistry, which are so much part of our modern society. Recall that it was Ernest Rutherford, the British physicist, who discovered the nucleus of the atom. Remember his experiment. He fired what I called atomic bullets at a piece of gold foil. Now, most of those atomic bullets passed right through the gold foil and were collected by a detector. But about 1 in 1,000 showed the remarkable and curious property that it bounced back towards the source. It deflected off something. And it was this unexpected recoil that led Rutherford to suggest that there must be some small, massive, charged particle at the center of every atom. That's the atomic nucleus. So in this lecture, we're going to review some of the properties of the nucleus, and I think it best to begin by looking at the cast of players. First, we have the protons. Protons are positively charged particles. They have a mass about 1,836 times the mass of the electron. So when you pick up any object, the electrons are negligible compared to the protons. Protons are probably represent 99.99% of the mass of most of these objects. The number of protons in an atom, then, is the atomic number. And the atom's position in the periodic table is reflected by that number of protons. Hydrogen, element 1, has 1 proton. Gold, element 79, has 79 protons. And indeed, the names we give to elements are merely a convenient shorthand for the number of protons that the atom contains. Single isolated protons are also called hydrogen ions. Now that may seem surprising, but remember what the hydrogen atom is. The hydrogen atom is a proton with 1 electron surrounding it. If you strip away the electron, all you have left is a proton. So these hydrogen ions, H+, are simply protons. Isolated protons are stable. They're stable particles in many of our everyday experiences. Remember, we talked about acids. An acid is merely water that contains an excess of protons floating around in the material, and that gives the material its acidic quality. it was relatively easy to discover the mass and the other properties of electrons and of protons because they're electrically charged particles. And electrically charged particles interact strongly with other charged particles. They don't penetrate matter very deeply. They can be detected. They can also be bent. Their paths can be bent in a strong magnetic field because, remember, magnetic fields influence electrically charged particles. So electrons and protons were easy to study. But it was curious because it was found out that atoms typically have a mass that's more than twice the mass of the electrons plus the protons. And this led scientists to speculate about the existence of another massive nuclear particle, one that has no electrical charge and therefore is much more difficult to detect. In fact, it wasn't until 1932 that British physicist James Chadwick discovered the neutron. He conducted experiments very similar to those of Rutherford. In Chadwick's case, he fired his atomic bullets at the element beryllium, not gold. And the resulting collisions produced a new kind of particle that was just as massive as the proton, but it penetrated through several inches of lead. Now, if you can take a particle and penetrate several inches of lead, it implies, first of all, that the particle is moving very fast, and second of all, that the particle is electrically neutral. It has neither a positive nor a negative charge. So Chadwick found that the neutron is indeed electrically neutral, and he also found that its mass is slightly greater than that of the proton. It turns out that isolated neutrons are not stable. They spontaneously transform into a proton plus an electron. So you have a positive and a negative charge balancing each other. A neutron then becomes two new particles. If you have a collection of neutrons, about half of them will transform to a proton plus an electron every 11.5 minutes. That's called the neutron's half-life. While the number of protons for any given element is fixed, the number of protons defines what the element is, the number of neutrons can vary. So, for example, carbon is element 6. Carbon always has 6 protons, but it can have 6 neutrons, it can have 7 neutrons. In some cases, it has 8 neutrons. Hydrogen is another case, and this is a special case because in hydrogen, these different numbers of neutrons give the hydrogen atoms different names. This is the only case where that's true. Hydrogen is typically a single proton with no neutrons. And then you have deuterium, which is 1 proton and 1 neutron. And you have tritium, which is 1 proton and 2 neutrons, essentially hydrogen with 3 nuclear particles. What we find is that the heavier elements typically have far more neutrons than protons. And this is partly, you can think of this as a kind of spacer. The neutrons help to spread out the positive charges of the various protons so you don't have as much electrostatic repulsion. Well, now that we've reviewed this cast of characters, the protons and the neutrons, let's think in a little more detail about how we name atoms. First of all, think about the periodic table. If you know the number of protons, you can name the element. As I've said, any element with 6 protons is going to be carbon. Any element with 89 will have a different name, or 73, or 24. The number of protons defines the element on the periodic table. Now, if we know the number of protons and the number of electrons, you can name the ion. Remember, the ion is a charged particle. So if the number of protons and electrons are equal, you have a neutral atom. If you have more electrons than protons, you have a negative ion. If you have more protons than electrons, you have a positive ion. And now we come to the neutrons. If we know both the number of protons and neutrons, we can name the isotope. Indeed, an isotope is an atom for which you know both the number of protons and neutrons. If you have a carbon atom with 6 neutrons, we call that carbon 12. And that 12 is called the isotope number. It's the number of protons plus neutrons. Carbon has 6 protons. Carbon 12 has 6 protons and 6 neutrons. But we also have carbon 13 with 7 neutrons. Carbon 14 with 8 neutrons. A very special and important isotope is iron 56. Iron is element 26, so it has 26 protons. Iron 56 then has 30 neutrons. and we'll find out its significance in stellar evolution a little bit later. But keep that one in mind, iron 56, and we'll talk about other isotopes as well. Now, remember that protons determine the chemical behavior of an element. That's the number of positive charges. It controls the number of negative electrons, and electrons are the things that bond. So the number of protons is very important in chemistry. Neutrons play no significant role in chemistry. They're neutral particles. All they do is make the atoms heavier. But neutrons play the decisive role in nuclear physics. All known combinations of protons and neutrons in an atomic nucleus are summarized on something called the table of the isotopes. The table of the isotopes is to nuclear chemists what the periodic table is to run-of-the-mill chemists. The table lists the number of protons on the vertical scale. So as you go from the first to the second to the third row, you're going up the periodic table. The first row at the bottom of the table is hydrogen, the second one is helium, and so forth, right on up for the number of protons tells you the name of the element. The horizontal scale indicates the number of neutrons. So for any given element, if you have several different possible numbers of neutrons, then you have several different boxes on this chart of the isotopes. Indeed, as you go towards elements with 40, 50, or 60 protons, you see numerous combinations of neutrons, sometimes 30, sometimes 40 different isotopes for a given element. All told, there are about 2,000 known isotopes shown on this chart of the isotopes. It's interesting that for lighter isotopes, the number of protons and the number of neutrons are usually quite similar. For example, you have carbon-12 is a common element, 6 plus 6. Oxygen 16, 8 and 8, and so forth. But when you get to heavier isotopes, they usually have far more neutrons than protons. The commonest gold isotope, for example, gold-197, has 79 protons and 118 neutrons. That's 50% more neutrons than protons. Well, this tendency means that for light elements, all of the items on the chart of the isotopes seem to lie close to a 45-degree line. But as you get to heavier and heavier elements, they fall off that 45-degree line. And one way to think about this situation, as I've mentioned, is that the positive protons repel each other. As you put more and more protons into a nucleus, you need more and more spacers, more neutrons to help stabilize that nucleus. One very useful way to think about isotopes is to think about their ultimate fates. In fact, isotopes can have several different fates, and I'm going to talk about 4 of these. In this lecture, I'm going to look at stable isotopes and radioactive isotopes. In the next lecture, we'll look at nuclear fission and nuclear fusion reactions, 2 other fates of isotopes. Almost every atom around us is a stable isotope. These are atoms whose nuclei are going to remain unchanged for billions upon billions of years. Hydrogen is a stable isotope. Carbon-12, oxygen-16, silicon-28, iron-56. These are elements once formed, once those isotopes are created, they really have no incentive to change. They are stable. It's certainly true that isotopes can be altered in highly energetic nuclear reactions, which we'll talk about in the next lecture. And so we have fission and fusion reactions. But there is a small fraction, perhaps 1 atom in a million in our everyday surroundings, that are radioactive. These atoms can transform suddenly as a result of spontaneous changes in the nucleus. Indeed, radioactivity is defined as the ability of some nuclei to change spontaneously, emitting high-energy radiation. The surprising phenomena of radioactivity was discovered quite by accident by the French chemist Antoine-Henri Becquerel, who lived from 1852 to 1908. He was one of the many chemists who analyzed rare minerals in the search for new elements. Now recall the importance of mineralogy in early chemistry. Even Dmitry Mendeleev cut his eye teeth in chemistry by analyzing minerals, and most of the new elements were found by analyzing rare minerals from obscure mines. Well, Becquerel focused on ores of uranium from mines in Saxony and Bohemia, where many exotic minerals came. One day he put some of his mineral specimens in a drawer, and also in that drawer was a photographic plate, an undeveloped plate, And coincidentally, there was a coin sitting on top of the photographic plate. When he eventually went to develop that photographic plate, he found that the film had been fogged up, but there was a clear silhouette of the round coin on top of the photographic plate. The inevitable conclusion was that there's some substance in the mineral that emits a strange form of energy, something that would fog the plate, pass right through black paper, but wouldn't pass through the coin. Well, once that strange phenomenon was discovered, there was an intensive effort undertaken by chemists around the world to isolate the radiation-producing substance. By far the most famous and successful of these chemists was Marie Sklodowska-Curie, who lived from 1867 to 1934. She was born Marie Sklodowska in Poland. She was a brilliant student, but she was unable to advance in the rigid Polish science hierarchy. She was denied the chance to do research in that country. Her fortunes changed dramatically when she came to live with her sister in Paris. There she met Pierre Curie, and their careers were intertwined until his tragic and untimely death in a carriage accident in 1906. Marie worked with her husband in his laboratory in Paris. She conducted her research under terrible conditions, it said. Apparently the lab was cold, it was leaky, it was improperly ventilated, partly because of the resistance of her male colleagues to provide her any support. Well, through the years, the Curies refined tons of high-grade uranium ores from Bohemian mines. Eventually, in 1898, they extracted small quantities of the previously unknown elements, polonium and radium, two radioactive elements. Her remarkable sample of 22 grams of radium chloride became the international standard for radiation units. Indeed, that unit is now called the Curie in their honor. If you look at the periodic table, you'll see radium lies along the alkaline earths. It's below barium. And just like calcium and strontium and barium, it forms a 1:2 ratio with the halogens. It forms ionic bonds, and so you form radium dichloride, which is that international standard. So the chemistry of radium was well understood because it was part of a group of elements that had already been well described. Marie Curie was awarded the Nobel Prize in both physics in 1903 and in chemistry in 1911. In fact, she's the only person ever to win both physics and chemistry Nobels. But believe it or not, she was denied membership in the French Academy of Sciences by one vote in blind balloting. There was such resistance to a woman being a scientist. Her husband also received the Nobel Prize in physics, as did their daughter and is their son-in-law in separate discoveries. Marie Curie died in 1934 of cancer that was undoubtedly caused by her extensive cumulative exposure to this high-energy radiation source. Well, the work of the Curies and others provided a wonderful set of samples for study. And so research on radioactive elements from minerals led to the discovery soon of 3 distinct kinds of radioactive decay. These types are called alpha, beta, and gamma in the order of their discovery. In alpha decay, an atom spontaneously releases a fast-moving particle, and that particle is composed of 2 protons and 2 neutrons. Think about a particle that's composed of 2 protons and 2 neutrons. It looks just like a nucleus. In fact, it is the nucleus of a helium-4 atom. 2 protons is helium, plus 2 neutrons gives you helium-4. So basically what you're doing is you're emitting a helium nucleus, which then quickly becomes a helium atom and floats around the atmosphere as a gas. Ernest Rutherford, in fact, identified this radiation, this alpha radiation, by sealing a small amount of radioactive material in a tube, and he came back several months later and found that the tube had been enriched in helium, which wasn't there before. Rutherford won the Nobel Prize for this work, and that's interesting, as several years before his discovery of the nucleus. In fact, the alpha particles were his atomic bullets in the experiments where he discovered the nucleus. Rutherford's probably the only person ever to have made his most significant discovery, the discovery of the nucleus, after he won the Nobel Prize. Well, after an alpha decay, an atom has 2 fewer protons and 2 fewer neutrons. That particle flies out of the nucleus. So think about what happens. The particle must transform to a different element. You lose 2 protons, so you have to drop back 2 places in the periodic table, sort of like a board game. For example, radium-226 decays to radium-235. 222. And so you see an element radium transforming, dropping back 2 places, and going all the way across the periodic table to radon. And every time you have alpha decay, you have to drop back 2 places, just like that. Now, alpha particles carry lots of energy, and this energy is converted to heat as the particles collide with their surroundings. Indeed, much of the Earth's geothermal heat is provided by alpha radiation being released from radioactive isotopes deep in the Earth. Alpha particles also carry enough energy that they can damage biological materials, and so they're quite dangerous. Second kind of radiation is beta radiation. And beta radiation produces high-energy electrons, what are called beta rays. So this is a much lighter kind of radioactive particle. In this curious process, a neutron spontaneously changes to a proton plus this high, fast-moving electron that speeds away from the atom. Now, think about this. Isolated neutrons, remember we said they're radioactive? A neutron changes to a proton plus an electron. So basically, beta decay is just what happens to an isolated neutron. When this decay process was first studied, researchers found that the energies of the decay products didn't quite add up. And this led to another important discovery. In other words, the total mass of the proton and the electron afterwards, compared to the neutron and the energy released, just wasn't quite enough to make up for Einstein's equation, energy equals mass times the speed of light squared. There had to be another source of energy. There had to be another particle. And this was how the neutrino was discovered. The neutrino, as we'll see later, is an important kind of particle which is emitted many by the sun and also has other properties which make it very interesting in the study of the universe and the universe's origin. We'll learn more about that in lecture 33. Well, think about beta decay. If a neutron becomes a proton, then the atomic number has to increase by 1. And so once again, we move around on the periodic table. For example, one very common kind of beta decay is carbon-14, which undergoes beta decay to nitrogen. And so you go from element 6 with 6 protons to element 7 with 7 protons. Carbon becomes a nitrogen in a magical transformation. Now finally, the third kind of radiation. Some isotopes undergo gamma decay. They spontaneously emit a high-energy electromagnetic radiation. Recall the electromagnetic spectrum. They're all different wavelengths of electromagnetic waves. And the highest energy waves we called gamma radiation. That's because nuclear processes are so energetic. In this particular case, the electromagnetic radiation is emitted as a result of an excited state of a proton. Now we have to go back. Let's think about how electromagnetic radiation was produced by electrons. In the Bohr atom, you had an electron in a ground state. If you excited that electron to an excited state and it dropped back down, you emitted a photon, typically of visible light, which is why many materials in our everyday world are colored. The energies of the nucleus are so much higher that when a proton is in its ground state, moves into an excited state, and then drops back down to the ground state, the energy of electromagnetic radiation that's released is much higher, and that's the gamma radiation. Remember, the gamma radiation, since it's just the emission of a photon, doesn't change the isotope at all. The number of protons is the same, the number of neutrons is the same, but still gamma radiation is high intensity, very potentially damaging radiation. So to summarize the 3 kinds of radioactivity, we have alpha radiation, the emission of an alpha particle, 2 protons and 2 neutrons, and the element drops down 2 places in the periodic table. You have beta radiation, a transfer of a neutron into a proton plus an electron, so you bounce up 1 place in the periodic table. And then finally, gamma radiation, the emission of a photon. All 3 kinds of radiation have penetrating power. They have energy, and they can transfer energy, for example, to biological systems. The alpha particle is a big, massive particle. It's like slugging something with a big fist. It's like and it doesn't penetrate very far as a result. The beta radiation, that electron can penetrate farther, it can go deeper into your tissues before it stops. And the gamma ray often passes right through your body because it's so small and energetic. But all 3 can do damage if the energy is absorbed by your body. Well, now that we've reviewed these 3 kinds of radioactive decay, I want to tell you about two fascinating and very important characteristics of radioactivity called the half-life and decay chains. First, I want to talk about half-life. That's a measure of how rapidly a collection of radioactive atoms decay. If you take a closer look at the table of the isotopes, you'll see with the protons in the vertical scale and the neutrons in the horizontal scale that every isotope is either stable or radioactive. Now, the vast majority of atoms in our environment are stable, of course, but the radioactive isotopes are the vast majority of known isotopes. Certainly 90% of all the known isotopes are radioactive. And the half-life is the time that, on average, it takes for half of that collection of isotopes to decay. For example, if I give you 1 million atoms of an isotope with a half-life of 1 day, if you come back in 24 hours, there are only going to be 500,000 of those radioactive isotopes left. A day later, there are only going to be 250,000. And each subsequent day, half of that collection, on average, will have decayed. These half-lives are extremely important for radiometric dating. You can date the age of an object if you know, first, the number of radioactive isotopes that you started with, their half-life, and finally, the number that you ended with. It's like a ticking clock inside the sample that you hold. A good example is carbon-14 dating. For example, you may have heard of the Shroud of Turin. This was dated by carbon-14 dating. Carbon-14 has a half-life of 5,000 years. And every living thing, as it takes in carbon, it turns out takes in a small fraction, about 1 atom in 1 million of carbon-14. So as long as you're alive, 1 atom in 1 million of your body is carbon-14. But as soon as you die, as soon as any living thing dies, that's plant material that makes paper or leather or wood or whatever, as soon as it dies, the clock starts ticking because the carbon-14 starts decaying. After 5,000 years, you have only half as much carbon-14. After 10,000 years, only 1/4 as much, and so forth. And so you can date objects by measuring how many carbon-14 atoms are left. In the case of the Shroud of Turin, it turned out that that burial cloth made of linen, a plant material, was only a little more than 1,000 years old, and therefore it was very unlikely that it was the burial cloth of Jesus, although it's a very beautiful artifact, no question. A second key concept related to radioactivity is the decay chain, which is a connected sequence of radioactive events. I want you to think about what happens when a radioactive isotope undergoes alpha or beta decay. You form a new isotope of a new element, and very commonly, almost always, that new isotope is going to be radioactive also. So one isotope decays, it leads to another radioactive isotope, that leads to another and another and another in what's called a decay chain. Now, by far the most common radioactive isotope in our surroundings is uranium-238, which represents about 1 atom in every 2 million in rocks and soil. All around you, there are radioactive isotopes all around you all the time. You can't get away from them. Well, uranium-238 has a very long half-life, about 4.5 billion years, and that's why there's still so much of it around from the origin of the Earth. Well, uranium-238 undergoes alpha decay, and it decays in a single step down to thorium-234. You've lost 2 protons, you've lost 2 neutrons, and you've changed the element from uranium back 2 places in the periodic table to thorium. The half-life of thorium-234 is just 24 days, and it decays by beta decay up to proactinium with a half-life of just about 7 hours, and then back up to uranium-234. Now here we've gone in 3 steps, in 3 moves in our game of isotopes, an alpha and 2 betas, from uranium-238 to uranium-234. Same element, but a new isotope with 4 fewer neutrons in this case. After 3 more alpha decays, we come to radon-222, and something very new happens. All the previous elements that I've described in this decay chain are metals, and they bond very easily in minerals. They become part of the soil, they're locked in the soil through chemical bonds. But think about what happens when you hit radon. Radon, element 88, is an inert gas. And an inert gas bonds to nothing. So all of a sudden, this atom is released from the soil, it's released from the rock, it goes up, it floats around, for example, in your basement. And if your basement is well insulated, if it's well sealed, radon concentrations can build up. Well, the true concern about radon, and the reason that you might want to go and buy a radon test kit to test your own basement, is that this radioactive isotope goes through a number of transformations. Very, very quick transformations. In a few minutes, it transforms to another isotope, and then another one, and another one, and another one, through a cascade of 8 radioactive events, each one of which adds radioactivity to your home's environment. This is why radon is such a concern. In this lecture, we've seen that neutrons add great variety and great interest to the world of the atom. The neutron defines the isotope, of which there are more than 2,000 listed in the table of the isotopes. Many of these isotopes are radioactive, and they undergo spontaneous changes that emit alpha radiation, beta radiation, and gamma radiation. Even so, the energy released during radioactive decay is far less than the energy available in the nucleus, the energy that's released by nuclear fission and fusion reactions, which we'll discuss in the next lecture.